Okay, so we're going to continue our discussion about electromagnetic waves. They're really important to astronomy because we obviously can't go visit other stars and other galaxies and things like that. So a lot of the information that we know about stars and galaxies come from analyzing the spectra that we detect from those objects. Okay, so now we need to talk about something called the Doppler effect. Okay, the Doppler effect is an observed change in the frequency or the wavelength of an object because that object is moving. And you've actually experienced the Doppler effect. You probably didn't know what it was called, but let's say that you are walking down a sidewalk or standing on a sidewalk and there's an ambulance approaching and then it passes you. You know that the siren to your ear is high pitched as it approaches and then it's lower pitch as it passes you. That is because sound waves are subject to the Doppler effect just like light waves are. And the sound waves that are emitted out in front of the ambulance are compressed and are closer together. Their wavelengths are shorter because the object that's emitting those is also moving in that direction. So they kind of get squished up together. So the wavelength here is shorter. And for sound waves, shorter wavelengths are interpreted by your ear as higher pitch. Okay, and then as the ambulance passes, the object making the sound is moving away, and the sound waves that are coming back to your ear are having to move in the opposite direction, so they're more spread out. And so your ear interprets longer wavelengths as low pitch. That's why the pitch changes as the ambulance passes you. And it doesn't even have to be an ambulance. If you've stood on the side of the road and you've had a car approach, you hear that sort of and you hear that pitch change as the car passes you. It's the same thing. It's Doppler effect. Okay, so the change in pitch, sound-wise, is similar to what's going to happen with light. So obviously light is not going to be interpreted as sound, but we are going to see the Doppler effect affecting light waves as well. So let's look at that. Okay, we've talked briefly about if you looked at a spectrum, the longest wavelength that we can see visually is red, and the shortest wavelength that we can see is violet. Well, violet is pretty close to blue on the rainbow, so we just worry about the blue end of the spectrum and the red end of the spectrum. Red is the long wavelength end, blue is the short wavelength end. Okay? When a star is moving towards Earth, then the light waves that it's giving off are a little bit squished. They're a little bit higher frequency and shorter wavelength than they normally would be. And so we say that a blue shift occurs because everything, the spectra from that star is shifted towards the high frequency short wavelength end of the spectrum, and that's blue for us. When a star is moving away from Earth, then the wavelengths are stretched out a little bit, and that would mean that they're a little bit longer than they normally should be. And remember that long wavelengths for us get interpreted as red, so it shifts towards the red end of the spectrum. Okay, so we talk about a red shift and a blue shift. Okay, so for instance, down here, where it says visualize it, here is your standard emission spectrum of hydrogen. Okay, and the absorption spectrum that they show you is very similar. You can see the major bars. Here's the emission spectrum of hydrogen. The absorption spectrum is sort of, the flip-flop, the opposite. And you can tell that there's a bar here, and it's a little bit further to the red end of the spectrum than it really should be. It should be probably about here. Okay, and this dark green bar corresponds to this. It's shifted a little bit towards this end, the red end of the spectrum. So all of these little bars, these distinct bars that tell us it's hydrogen, they all get shifted a little bit to the left, or the long wavelength end, and that's the red end. Okay, this is if the object is moving away from us. Okay, everything gets shifted that way. If an object is moving towards us, we're going to have just the opposite. Okay, normally the line should be here, and we notice that it's shifted a little bit to this end of the spectrum, and that's the blue end of the spectrum. Okay, because there's the bar. Okay, here's the green, and again, it's shifted a little bit this way. Okay, and things are going to shift towards the short or blue end of the spectrum when they're being compressed because the object's moving towards us. Okay, so many of you guys have posted questions about, how do we know all this stuff about stars? Well, this is a lot of how we find things out. We can use the spectrums from those stars to figure out what they're made of, because like I said, every element has its own unique spectrum. And then we can recognize, for instance, they know this pattern means that it's hydrogen, but the bars aren't quite where they're supposed to be because they've all been shifted one way or the other. Okay, so we can figure out whether that object is moving towards us or away from us. And how big of a shift, how much it's moved one way or the other, is going to tell us how fast that object is moving towards us or away from us. So there's really a lot of things that scientists can find out just by analyzing the spectrum of light from an object that's coming in. Okay, so just a reminder, with sound, this is what you're more familiar with as far as Doppler effect. You've heard that change in pitch as a car, for instance, approaches and then leaves. It changes pitch. Okay, it goes from high pitch to low pitch. Okay, high pitch because the waves are compressed as they approach you. Low pitch because the object then moves away from you and the sound waves coming back to you are more spread out. Okay, with light, the Doppler effect causes a change in color. Okay, those emission spectra bars are shifted towards the red end of the spectrum if the object's moving away, and they're shifted towards the blue end of the spectrum if the object is approaching. This funny looking little thing is a Greek letter lambda, and it just is what scientists use to represent the word wavelength. So this really says emission spectra bars are shifted towards the red or the longer wavelengths if moving away, and towards the blue or shorter wavelengths if they're approaching.